A doutora Reenie Parris, que é uma especialista mundialmente conhecida, que atua nessa área de medições, tanto a parte, digamos, do controle, né, de um controle total aí no processo de medição, que tem muitas interferências, então conhecer cada parte, o que acontece, qual é a segurança que nós temos com esse resultado, é extremamente importante. E a doutora Reenie Parris atua no NIST também já há bastante tempo, mas dentro do nosso acordo de não entrar no tempo, também não vou dizer. E ela tem uma participação no CCQM, o Comitê Consultivo para a Quantidade de Matéria. Ela trabalha muito na parte dos ensaios de proficiência, estudos de comparação interlaboratorial, né? Pois um programa de comparação interlaboratorial não é só a questão da proficiência em si, e para atender a 17025 muitas vezes é citado. Ele tem vários recursos que nos podem apoiar no desenvolvimento de metodologias, na validação, e no controle, no conhecimento do processo, de uma amostragem, a influência de uma amostragem, enfim, é um espectro bastante amplo. E ela tem um domínio ímpar nessa área, que foi o motivo do convite que fizemos a ela. So, dear Reenie, thank you very much again, and the floor is yours. Thank you.
Thanks, Vera. Can you hear me okay?
Yes, very clear.
Okay, good, good. Well, thank you very much for inviting me to participate in your conference, and I'm very sorry I'm not there in person to be in Brazil and to see all my Brazilian friends. And so, as Vera, I think, said, I'm going to be talking about metrology in support of competitiveness and innovation. And I'll be giving the world view, and then Valnang will give the national view.
Okay.
Okay?
Yes, sure.
So, today I'm going to talk about the need for acceptability and confidence in chemical measurements provided on the global scene, tools and mechanisms for providing acceptability and confidence in measurement results, and examples of impact on innovation, competitiveness, and credibility if laboratories' measurements do not provide this confidence. And then I'll intermix with this, I'll talk about some of the current issues under discussion at the global level. So the need for metrology has been recognized through the ages. We've long recognized the need for measurement science and standards to support construction and manufacturing and trade. Metrological traceability, we often think of it in terms of being provided as traceable to the SI units through RMOs and national metrology institutes, such as NIST and in Metro, and then you have private and state lab measurements, or reference laboratories sometimes at that point, and then field measurements. And this traceability to the SI and global comparability are a basis for mutual recognition and international trade and confidence in data used in making decisions relating to health, safety, commerce, and or scientific excellence. So it's a way, it's not the only way. So just some definitions here. I think you've seen them in the most recent VIM. What used to be called traceability is now called metrological traceability, and that's there. It's a measurement result that can be related to a stated reference through a documented, unbroken chain of calibrations. And note the difference here. We used to get questions when we first started doing here between the use of metrological traceability and the term relating to traceability of products. Both refer to a pedigree, but one refers to metrological criteria and the other like a chain of custody of a sample. And then commutability has to do with when you make a particular reference material, are your expectations that it will behave in the same way as the real sample that you're trying to analyze. So as I said, traceability to stated references, whether it's to the SI or to a particular process, and global confidence are a basis for mutual recognition and confidence. And it's more efficient if we all provide traceability up through the SI instead of every customer having to do comparability measurements with every buyer. We can have confidence in the measurements that each of us are making. Early drivers for standards in the U.S. had to do with out-of-town fire companies arriving at a fire, and they couldn't connect their water hoses to the water hydrants because they had different standards, different sizes. And so they adopted a coupling standard that would get rid of that problem. And then we started having standard samples programs, the original reference materials, and they had standardized irons, which had to do with the people who were manufacturing things. So today we have more than 1,400 different NIST SRMs and sell about 30,000 a year. So why do we need to have our measurements to be comparable? We need them for international acceptance and confidence in the measurement services. I had a guy here that sells chickens, and he was complaining, this was a long time ago, that his chickens were sitting on the docks in Russia where they had to wait for them to be retested. And they were losing weight, and they were getting older, so they were losing value. And so it's important for fair trade, for trade agreements, for various worldwide services, global issues such as environmental decision-making, assessment of food safety and nutrition, all kinds of decisions that have to be made based on measurements. Accreditation agreements, metrological agreements. Our goal is to, once measured or tested, it's everywhere accepted, so you don't have to have this duplication of effort. The impact of having these measurements and standards program, there's approximately $500 million per year NIST investment in our measurement standards programs. And it undergirds, it supports about $10 billion per year of private sector investment in measurements and standards. And it impacts our U.S. economy. It's been estimated that more than half of the U.S. GDP is supported by measurements. So it's vital for commerce and international trade. It drives demand for new measurements and standards, and we have to maintain state-of-the-art scientific facilities because there's always a new type of thing that people are wanting to measure. Why SI traceability? Well, you can do some comparisons, and we used to relay them back to a particular material or just to one material that everybody had in that they had in common. But if you do it to the SI, it can be stable and it can be related over time to measurements in another laboratory. It's comparable in that results of measurements of the same quantity will be comparable over time and space, and coherent in that it'll be the same over both time and space. So traceability to the SI provides all three of these, and other approaches typically only provide the first two. Okay, the meter convention, the Treaty of the Meter we all heard about when we were in our chemistry class in colleges, is a worldwide, it provides an infrastructure for measurements, both physical measurements and chemical measurements. And in 1999, they developed the CIP Mutual Recognition Agreement. It was done in 1999, and it provides an open, transparent, and comprehensive system for vetting the calibration and measurement capabilities that upend services that where the we are the National Metrology Institutes there. I don't know if you can see my pointer on the screen or not, but it's in the lower right in red, where the place in the role of the National Metrology Institutes in this. And we can no longer ask customers to trust us. We're from your NMI, but we have to show them and demonstrate so they will have confidence in the measurements we make at a high level for doing certified reference materials and various types of activities. So as I said, it was established there was a growing need for an open, transparent, and comprehensive scheme to give users reliable quantitative information on the comparability of the national metrology services. And they, in turn, then would establish comparability with other regional labs and testing labs and field labs in their countries. And it provides a technical basis for wider agreements for international trade, for commerce, and regulatory affairs. It requires three things. It requires us each NMI or designated institute to declare and document calibration and measurement capabilities. And we refer to those as CMCs. And there's an open database on the web. I'll show you a slide a little bit that talks about that. We have evidence of successful participation in formal, relevant international comparisons. And these are comparisons with our peers, those who are providing a traceability linkage to those in their country and to those elsewhere. You can get traceability through NMIs of other countries as well. And then they have to assess the quality system of each NMI's measurement services, because we do these international comparisons periodically, but you need the quality system to link it together over time. So ideally, a National Metrology Institute or an officially designated laboratory is seen as its country's ultimate reference point for measurements and standards to support all kinds of measurements needed within the country. And it usually has some enabling legislation in support of this role that is recognized within its country. And then we have our programs well aligned with our country's strategic priorities. There may be standard reference materials that we need in the U.S. that are not needed in other countries, and likewise in your country. You may have special needs. So typically, the role of an NMI, we have scientifically sound, metrologically based competencies and measurement capabilities that are internationally vetted and recognized. And then we provide this traceability linkages to our customers via validated reference methods or certified reference materials or value assignment of customer-provided samples, including proficiency testing samples. There's reference data, all kinds of things there. So NMIs around the world have programs focused on physical metrology, and a smaller number have programs for chemistry, and an even smaller have them for biological measurements. And they are now working together to link our measurement system to the fundamental constants of nature. So this is one of the things that's changing at the international level. They are working at redefining the kilogram and the mole, both of which are used when we're talking about chemical measurements. But the definition in practice will not change the work of our analytical chemistry and things like that. It's such a small kind of a change. So if there's more if you want more information about this, you can contact either your representatives to the CIPM, or you can contact me. So rigorous realization of these units has undeniable impact on trade, commerce, and quality of life. Now, more and more, in addition to supporting the realization of those SI units, we are finding ourselves focusing increasing amounts of our research and measurement service activities on quality of life and economic and social sustainability, environmental issues, food issues, those innovation, things that are needed in those areas. And we often work and complement the support of missions of other national governmental agencies. For example, in the U.S., we have an Environmental Protection Agency, and they protect human health and safeguard the natural environment. And NIST does things in the environment, but our role is to support the measurements needed by EPA to realize their mission, whether it be developing new methods or providing standards for measurement infrastructure or whatever is needed. And likewise with our health institutes, we assist them and provide services in the measurement areas. We don't define their priorities or what is needed to be measured or what the limits are. And you see all kinds of headlines in the areas of chemical metrology. We often talk about this as metrology for stuff, because you have time and length and temperature, but the chemistry and biology is all kinds of stuff. So these are just some headlines that we've seen, I guess, in the past few years. Now, there are challenges associated with chemical measurements in real samples. When we talk about making chemical measurements, we're not just talking about amount of substance, a quantity. We also have to define what it is we're measuring. And we're often tasked with accurately measuring practically nothing in the midst of everything else, without the benefit of absolute or quantum-based methods. There are many methods being used and many types of analytes and matrices. For metrology and chemistry, as I said, the task is to determine the quantity of a specific chemical entity and not just the amount of substance. And they're multidimensional here. You can see we have a whole range of mass fractions, who knows how many kinds of matrices, and the number of compounds being measured is immense. So put all those together, and then when you add in the biology, when they have to do structural kind of formations and things of that nature, it can get very complex. This is an example of just classes of chemicals in food that are regulated in the U.S. And you can see the different classes here. These aren't individual compounds. These are just classes. And the different range of concentrations and just how much there is to do in just the food area. And the biosciences, these life processes are very complex, and the information space is very vast. We used to do this Krebs cycle back even when I took microbiology in college, but it's not as simple as we once thought. So from a physical standpoint, a physical measurement, we're saying, what's the mass of Willie? And that would be a certain number of kilograms. In chemistry, you'd say how much cholesterol. You can't just say the unit, milligrams per deciliter. You have to say cholesterol is there in Willie's blood. And then from a biological standpoint, which cholesterol-lowering drug would be best for Willie in terms of both efficacy and potential side effects. And right now, that's a lot of trial and error, although they're beginning to identify various genes that can be indicators of whether you would get a side effect or it would be useful for you. And then for the measuring, even when you have the same measuring, say you're doing lead in a soil material or in a sediment, what's the assigned value meant to provide? You have to pick the right one to use in your quality control process. Do you want one that aims for the truth, the actual amount of lead that is in that soil material. Now, we never know what that is exactly, but the best realization of this would be in the SI units, in mole, kilogram, meter, moles per moles, gram per grams. Or you want what a standard method should get. And this would be method dependent. For example, it may only extract 85% of it out of the sediment. Well, not for lead, but it's a method-dependent value, and you were expected to do that. Often with the methods that NIST uses, where we are realizing to the best of our capabilities the SI units. If we took a proficiency test, or if we used a reference material where the results were based on a standard method, we'd get the wrong answer. So lead in the soil material as XX milligrams per kilogram, or lead by US EPA method YYY as that. And you have to be very careful in specifying this when you're a reference material provider, and you have to be careful as a user that you are picking the appropriate material for use in your quality control scheme. A global challenge is that we're seeing exponential increases in requests for CRMs and proficiency tests. And with that immense number of analyte matrix combination levels, how can we cover our measurement space effectively and efficiently? This is true for makers of certified reference materials, proficiency test samples, need calibration materials with assigned purity. It's not achievable for us in terms of PTs or reference materials to have a one-to-one match. So how do laboratories realize metrological traceability when they don't have a comparable CRM? What do various assessors expect and require? We're seeing a lot of conversations going on about this. So we need an efficient strategy so they can collectively establish maybe a virtual system that covers things, covers our measurement space. When you're doing a chemical measurement, you're usually doing a comparison of a known amount to an unknown amount. And you use typically a calibration curve where you put you make a known amount and check it versus the response of the instrument, and then get the response of the instrument to an unknown. So for this to be known, you can't just weigh it out and say it's certain milligrams. You need to be assured, either through your own measurements or the measurements of the material provider, that you have a good assessment of purity of that compound. And especially in the organic area, that is a critical aspect. Now, there's a CIPM Consultative Committee for Metrology and Chemistry and Biology. We're on that first chart I showed you about the meter convention, and this is one of the areas. And for the organic group, we have to run inner comparisons, and we need to cover all the space in which we need to be comparable with other NMIs. And we run different laboratory inner comparisons. So what we're doing in the organic group is to do a certain number of ones where we're looking at the primary calibrators, those neat materials that we weigh out, or either solutions that we get to provide calibration curves for our instruments. So we decided that in the for organic, the neat materials, the calibration materials, that molecular weight and the polarity were important indicators. So we took this space and we divided it into 6 sections: a low polarity, high molecular weight, a high polarity, high molecular weight. You can see these 6 classes. And then we're trying to do a comparison of materials in each of these sectors. The reference being, or the implication being, that if you do one appropriately in this sector, you will be able to do others appropriately in that sector. So that's how we're doing that. And this just shows some of our schedules for doing primary calibrants, because we're here to do a lot of reference materials. We're not here to only run interlaboratory comparisons with each other. And then for the accuracy matrix based, we look at polarity, and then we also look at the various kinds of matrices, and we look for ones that probably are more difficult sometimes than others, because if you can do the harder one, you can do the easier one. So, in example, I showed you all those food areas, and what has been done is there's a triangle that's been established, and at the corners you have, this one has 0 protein and 100% fat. The lower left has 0% fat and 100% carbohydrates. And on the right bottom, it has 100% protein and 0% carbohydrates. So all foods would fit somewhere into these. So we have divided this into, AOAC actually developed this, and they made this into 9 sub-triangles according to the percent protein, fat, etc. And what we are trying to do is to do both reference materials and people doing PTs and people doing just different kinds of work, maybe for the assessors. If you do one appropriately in one of these sectors, it's assumed you can do the other one. So if you have a reference material that's in sector 1, say, it would be appropriate for other foods than that. So most labs provide analysis for a similar set of analytes to nutritional things and common contaminants, but a wide range of types. So the matrix differences and the concentration differences are the primary challenges here. So that's how we're handling that in the food area. And it may be that as time goes on, the assessors will begin to look at this, to look at your capabilities in handling a wider scope instead of just a particular matrix analyte combination. Now, there are many different providers and sources of reference materials and CRMs, but the use of the term certified reference material is not restricted and can be misused. So as users, one of the things you have to do is to make sure what the pedigree is of the material you are obtaining or preparing in-house yourself, and if it's appropriate for your needs. So NMIs can do it, reference laboratories, you have commercial providers of reference materials, a wide variety of people. Now, another thing that's going on in the on the global level is an update on the general guide standards that are applicable to reference materials. The following are being revised, and they're very close to being published. The ISO Guide 30, which is terms and definitions, ISO Guide 31, which is the contents of certificates and labels, and 33, the uses of certified reference materials. Because no matter how good it is, when it is produced, if you don't use it appropriately, both the traceability and your quality control can be meaningless. Now, being revised is ISO Guide 35, which is the general, the certification, the value assignment of reference materials. And they've just published Guide 80 on preparing in-house reference materials and the expectations of that. Guide 34 is being turned into a standard. It'll be ISO 17034 by a joint RIMCO-CASCO working group, and they're having their next meeting in October. So you can look on the internet and keep up to date. If you look on this website, you can see the current set of standards, whether they are published. They have a check mark here. I don't guess you can see this. And then it shows the ones that's under development. So that's a good site to go to. If you look in the guides and you look in the both the VIM as well, the vocabulary of international measurements. You'll see definitions for reference materials, and there are different ones for certified reference materials in the international vocabulary of terms in metrology versus those in the guides. And I know that NIST is using this first one when we are doing our reference materials at this point. So you can see those. Now, when you're going to make an SRM, when you're building a house, you just don't start pouring concrete or sawing woods and nailing it together. You need to know what you're building. Is it a country cottage? Is it a palace? Is it a warehouse? What is it? You need to know what the building is going to be used for. You need a plan. And what constraints do you have? You know, if you only have $100,000, you can't build a $3 million facility. So the same way in value assigning a material, you just don't start in analyzing it. First you determine what's the analyte. What is it that needs to be measured and reported on here? What are your customers needing? Because if you don't do it in the form that they need, it'll be useless. What value are you going to have a best estimate of truth or a value obtained with a specific method? And what's the intended use of the value? What does the uncertainty need to be? How tight does the metrological traceability need to be? There's no one way of value assigning a material, but there are a number of appropriate ways, and you need to pick the best one based on your capabilities, your instrumentation, and what's needed. A number of approaches are used to certify values with the appropriate uncertainty in both CRMs and value assignments of PT materials. So you can have a known calculated value as if you gravimetrically prepare a neat material where you know the purity in a known mass of solvent, or you can do it by the validated reference procedures we talked about. You can use, that's where it's going back, it's been validated, say, to be traceable to the SI. You hear about primary methods, but it still needs to be validated that it's primary when used in your laboratory. There are many things that can cause you to get incorrect results, even if you're using a primary method. You could have lack of equilibrium, whatever. A measurement process, you can get consensus values from expert laboratories. That's the one that you get it, but it's good for that material, but it may not be comparable over time when you have a different set of expert laboratories. And certainly that applies to when you get consensus values from participant laboratories. And these different approaches will require different reference material provider competencies. If they're going to provide the reference value, they need to have their capabilities and be accredited, or somehow have you to have confidence in their analytical capabilities. If it's coming from participant laboratories, they just need to know how to do the statistics and enough scientific knowledge to be able to see if there are, any strange anomalies in the data. Now, back when I talked about the MRA, the Mutual Recognition Arrangement, and we talked about that the various national metrology institutes have to propose and get peer-reviewed and have published their capabilities. Well, that's called the Key Comparison Database, and this is the web page down on the lower left. And it has to do with national measurement standards and calibration and measurement certificates, our SRM certificates, CRM certificates, and that we are comparable with other laboratories. So you can do various types of searches on this. You can look to see who's participated in the first line there, the key comparisons that have been done. You can search for matrix or analyte or the various NMIs, and you can look for the CMCs, the measurement capabilities that have been approved for a particular NMI. Now, one of the reasons I was showing this here is that we talked about value assigning a material. Well, suppose you need a material and you don't have the capability in your country to do a PT, and you need to get someone else to do it for you. Well, when people do these capabilities and publish them, it talks about the matrix material, the analytic component, the mass fraction range, and the uncertainty. But it also lists mechanism for measurement service delivery. Now here, this is for Japan, and it's a CRM, a specific CRM, so you can use that for your quality assurance purposes. But now in the next one, their mechanism for measurement service delivery is for value assignment of proficiency testing samples. Now this one is for local testing laboratories, but many NMIs in other countries will do this. So you could pay them, and if they have their capability listed here, they have demonstrated that they can do this in a metrologically appropriate, traceable manner. And so for those, even reference materials, if you need a second value to compare with your own, or you need to find reference materials, this is just a good place to go to do that. They have various responsibilities. I'm running out of time, so I'm going to skip through that. So it's just critical to remember that you need to choose a reference material that's appropriate for intended use and recognized as appropriate by users of these materials and users of the data, your customers, for that. Now, metrology and its impact on innovation, commerce, economic and social sustainability. What happens if you don't have confidence in someone's measures? Some of the different scenarios I'm going to show here. Here is a proficiency test that was done for 10 in a frozen tomato paste. Now they used a consensus value, and the error is pointing here. And the orange shows a reference value assigned by an NMI, and it's traceable to the SI. And you can see those are kind of far apart. In fact, we show here the changes in ratings on a PT's performance if you use the reference value instead of a consensus value. And this would be more comparable over time to use this reference value. Now, so sometimes doing these proficiency tests provides a license for the customer to conduct business. So this can be a very critical thing. So if you're doing a PT and you haven't assigned an appropriate value, it can have a lot of consequences, negative consequences for your customers. In healthcare, lack of standards or lack of adhering to those standards can cost a lot of money. You can have to repeat measurements, do a lot of quality assurance. It can be very expensive. But it also affects quality of life. If you get the wrong results, you can get incorrect diagnosis and treatment, and it can impair the patient well-being if he gets a medicine he doesn't need. This is a bias in cholesterol measurement. Mayo Clinic took over 20,000 people, measured their cholesterol, and plotted them on here. So this is the cholesterol levels of 20,000 people. And then down here, they used this to show what would happen if measurement by it were 10%, 3%, or 1%. And it could make, at the 10% level, you could have 129 out of 1,000 people incorrectly diagnosed. So some people would not get medicine when they needed it, and some would get medicine they didn't need. So that's a critical thing that can happen if your measurements aren't comparable with those of others. When we look at food, we have 4 areas. You have contaminants, you have labeling, you have some indigenous contaminants. And some things are based on tariffs. It has to do with the value of the material based on its composition. This is one of Gabriela I see some of you know her, that she did for Chile, and she just did a scenario about economic losses due to the closure of international markets to Chilean exports because they were having some unreliable measurements. People didn't have confidence in them, so they were closing their ports to the big food exports that they were doing. And this just shows you some of its the monies that were lost to that country. You also could have a big loss in tourist trade if you have problems with water or something that goes undetected. I had this one twice. And then environmental is the same way. In all the different areas, it covers a wide range of things, but you can have very different things. This one's kind of old for us, but it was the last one I collected, so I put it on here. It was a New York, New Jersey waterway sediment. They were having trouble with contract laboratories. They were having a lot of false positives for things like DDT and things. And this was in a waterway that was used by ships. And they have to dredge those to remove the sediment at the bottom of those every so often so that the boats can continue to navigate in the waterway. So the impact that they were getting these analytical inaccuracies, if they got false positives, they thought they had a lot of contamination when they didn't. It required very expensive, unnecessary incineration or contamination. And if you had a false negative, you would get inappropriate disposal of contaminated material. So you had adverse health and environmental effects. Because if it didn't exceed limits, they would dump it in the ocean. And you can see here some of the cost of that. Now, as I talked back with the tariffs there, the value of a commodity is often determined by the amount of the major component or the amount of various impurities in the commodity, like precious metal, how much gold is in a gold sample. The amount of sulfur and moisture in crude oil is inversely related to its value, and so it has to be analyzed for that. There's about 161 different varieties, and these are some of the different types. And they have to do sulfur content by weight and acidity and moisture. And the prices vary widely on these. They estimate that each percentage point increase in sulfur decreases the value by 3%. So that's a case where if you were a producer and you were not doing your measurements correctly, it could cost you a lot of money, or you could sell it to somebody and they were not getting what they had bargained for. Now we'll get to innovation just a little bit. Sometimes you have new measurement technologies. We're always working to do things that we don't currently know how to measure. And often and for those to be accepted by the user community or by the users of the data, they need to have either appropriate reference materials or reference data, or they need a way to have confidence. When they started developing remote sensing here in the US so that you could look at a smokestack, for example, on an industrial site, and you didn't have to go on their property. Instead of having to climb up their smokestack and take a sample, you could stand on the fence line and it's ground-based, and you could take measurements based on spectroscopy and determine the concentration. And this only became accepted by community when NIST provided some standard reference data that would enable this to be calibrated appropriately. And they did round robins and demonstrated that it was appropriate. You also could see if it's coming from a particular smokestack or coming from somewhere else. So that is very useful, and it required measurements that provided confidence in order for this new innovation to be accepted. And it had a lot of good applications, but unless you have the measurement backup, it won't be accepted and used. There's emerging things with organic and flexible electronics manufacturing, and they are compatible with a lot of different displays and sensors and various kind of things, but it's hindered by poor reproducibility and highly process-dependent properties. So if you work at providing the measurement infrastructure for this, then you have a very good innovation that can be used by the public. So the innovations could be the measurement techniques themselves, or it could be the standards to support those innovations that allow them to be used efficiently and effectively in your country. So metrology pays a significant dividends. You have a program to a nation's economy and quality of life. And it impacts innovation, commerce, economic and social sustainability. And we sure have a lot of different things that we measure. So thanks for your attention. I've listed my email address and my phone number and then the NIST website, all of which you can get further information. So hopefully you've been able to see the slides okay. And again, I was sorry I couldn't attend in person. And I don't know if there's times for questions and comments or not.
Can you hear me, Dr. Reenie?
I can hear you.
Okay. First of all, thank you for your presentation and congratulations. It was very good for us in our Congress. And I would like to, let me see. First of all, you have said that the NIST, National Institute of Standards and Technology, supports the...
I can't hear you.
Sorry, can you hear me now?
Yes, can you just speak in the microphone, I guess?
Okay.
Yeah.
You said at the beginning of your presentation that the NIST supports U.S. Environmental Protection Agency regarding the assays and environmental assays that they need in general. So I would like to ask you if NIST does all the assays concerning the environmental assays, or they design other laboratories in the U.S. to do so after the needs of the U.S. Environmental Protection Agency.
Okay, I couldn't hear all of that. Are you asking how we prioritize our activities based on the different sectors?
Yes, if the National Institute of Standards and Technology, if you do all the needs that US EPA, or you assign other laboratories to do so in the US.
We don't do any of the regulatory. We are a non-regulatory agency. We work with EPA sets their what things they want to measure and what limits they want to measure it at and what. And likewise with manufacturers, with the National Institutes of Health, we work with the Center for Disease Control. They set the context of that, and they have priorities. Now, we also interact with many people in the public sector, in the private sector, different companies and all. And each year they will propose the types of reference materials, or where they will have a roadmap of where they see metrology needs being in the future. Sometimes we will bring together many people, like we did in the health sector, from many different stakeholders and get them to work together on helping us establish some priority of needs. But when it comes down to then working with whether we do, 14 environmental and 16 foods and some things in the manufacturing area and how we allocate the chemistry versus the physical. That all gets done at the NIST level. We have input from our president, our administrations, we have input from the agencies, and we have input from the private sector. And they can give us their top priorities, but when it comes to intermingling them, we do it ourselves. We increasingly are looking, when we do these comparisons with other countries, we try to see if there are other places that people can get support for doing this. And that also, or we look for things where it's a very mature area and maybe it can be handled by the private sector with appropriate traceability. So it's not an easy thing to do, but it's something we all have to do. And I see that often when I'm on a peer assessment there at various laboratories. Sometimes people don't do, you have to start there. You have to do a very good needs assessment and decide what is the most important thing for your country. And sometimes it's based on money, sometimes it's based on health considerations or a combination thereof. Did I answer your question?
Yes, yes. Thank you very much. Dr. Reenie, I have another question. You've shown us the difference between the results in a proficiency testing when we use as the assigned value the consensus value or the reference value. We know the importance of reliable result, and I work with a proficiency testing provider, and I know that it's difficult to establish a reliable assigned value when we use the value of the laboratories that participate. So how can I know if the assigned value established by the consensus, the values of the participants, how can I know if this value is reliable? Is there a minimum of participants to establish like a statistic significant value? Is there a minimum? I don't know if you could answer, please.
You asked about, okay, so if you're doing a consensus value, you want to know the minimum number of labs or something like that?
Yes.
Okay. A lot more depends on the capabilities of those labs. I would have a lot more confidence if instead of using the consensus value of everybody, if they would use a certain number of labs, maybe use the labs that were accredited for that measurement, or use labs that had demonstrated their proficiency in doing that. Especially if you're doing it by consensus for a method-dependent value, a result based on a specific method, it's important to have laboratories that have a lot of experience in performing that method. You don't want it just to be laboratories that are just doing it for the first time, because we've certainly seen that it gets better with practice. And they can be accredited for doing that particular method. So I've seen PTs done that way. If you're running the PT, you can do your own check, your own analysis of that if you have the capabilities to do that. You could also send it off, talk to someone that has that capability at an NMI level and see if they would do a check for you on that. Maybe you could pay them to do it, and that would provide more confidence to the people. Oftentimes, if somebody would run a reference material of a known value that's similar to that along with it and show those results, that would give you more confidence in the value, say, of those expert laboratories.
Okay, thank you. Thank you, Dr. Reenie. I'm sorry for my English. I'm out of practice. I'll pass to Dr. Vera. Thank you.